In fluid mechanics, when we start approaching a new flow, one of the critical questions we need to ask is that of turbulence. Specifically, is the flow going to be turbulent or not? Now, it's a critical question, but answering it is really not difficult. Let's take a look at it together. In a previous video, we have learned to recognize turbulence. We have said there are three important characteristics. One is that it's chaotic motion, which means a very small change in the initial conditions results in a large change in the specific configuration later. Second important characteristic, it's a breakdown of remaining scales. It means we're looking for large structures that become medium structures that become smaller structures. And lastly, turbulence is generated. It's not a magical, spontaneous phenomena. It requires energy, and then it dissipates this energy. Now, what we want to do today is to answer the question, is my flow going to be turbulent or not? And to do this, we want to quantify the Reynolds number. Reynolds number will not tell us how much turbulence there is, but its order of magnitude, how large this number is, how many digits it has, will tell us whether it's likely or not that the flow becomes turbulent. The Reynolds number is a conventional definition, and it's defined as rho v L divided by mu. Let's take it one step at a time. Rho is the density of the fluid, how many kilograms per meter cube you're going to find where you're looking. V is a representative velocity. I know that in any flow you're going to have many different velocities, and what you're trying to do here is to have a single value that represents all the velocities of the flow. Most typically you will take just the inlet velocity to your flow. L is the size of the largest flow structure you expect to see in the wake of your flow. Yes? So most typically, the largest flow structures you expect to see would be about the size of the biggest obstacle in your flow. So you take a representative length of the largest object you can see, or the largest diameter you can see, and that is a good length to take to quantify the Reynolds number. And lastly, the viscosity, as we have seen, is the stickiness of the flow and just a property of the fluid. I know this is incredibly frustrating when you read this for the first time. Look at this. Representative velocity. Largest expected flow structure. How frustratingly vague can this be? But you have to remember here, what we are looking for is an order of magnitude. Nobody is interested in a difference between a Reynolds number of 602 and 603. On the contrary, what we're looking for is how many digits does the Reynolds number have overall. A couple more points before we move on. First, the Reynolds number has no dimension. It is Pascal seconds on top, Pascal seconds on the bottom. The units all cancel out. We're going to see this is not an accident. It is by design. But we have a lot of videos to go through before we can show this. Second point is a recommendation. The Reynolds number is always written as an uppercase R, lowercase e, straight characters, not italics, and very often we use brackets. You can make up your own fancy notation for this at the risk of greatly annoying your colleagues. Here are a couple of examples of how to calculate the Reynolds number. This is a buoy in the river Elbe, just not too far from where I live. It's about this big, the buoy, and the flow comes from the left and leaves quite a turbulent wake behind it. What's the Reynolds number here? Let's take a look. Well, the density of water is 1,000 kilograms per meter cube. This is pretty straightforward. A representative velocity would be the velocity on average of the river at this point, which would be about 2 meters per second in this case. The size of the largest expected flow structure, you can take a guess at it by looking at the video. A good guess for that, a good reference for that, would be about the diameter of the buoy itself, and that is about 40 centimeters here, 0.4 meter. And lastly, the viscosity of the water is about 1 millipascal second, in this case 8.9 times 10 to the power minus 4 Pascal seconds. Put these together in a fraction, rho v L divided by mu, and you get, in the end, about 900,000. Again, no unit. The Reynolds number is just a ratio of parameters with no dimensions of itself. Let's take another example. Take a basketball in your hand and throw it into the net. The basketball moves through the air. What is the Reynolds number of the air around the basketball during the throw? Well, the density of the air outside, 1.2 kilograms per meter cube. A representative velocity is difficult to pick in this case because all the velocities are changing all the time. In this case, I chose the velocity of the ball at the top of the parabola, and that would be 8 meters per second approximately. The size of the largest flow structure, again, is the size of the ball, because this is the largest possible flow structure that you expect to meet in the turbulent wake behind the ball. In this case, I have to look it up. A basketball is about 75 centimeters in diameter. And lastly, the viscosity is the viscosity of the air, in this case 1.5 10 to the power minus 5 Pascal seconds. So let's put this all together now. Reynolds number, rho v L divided by mu, put all the numbers, paying attention to units, and then we get about 480,000, or about 500,000. So what do we do now with these numbers? Is my flow going to be turbulent or not? Well, the rules to decide this are very simple, very easy to remember. If your Reynolds number is 100 or less, then it's very likely it's going to remain laminar the whole time. And if your Reynolds number is 1,000 or more, then it's very likely it's going to be or become turbulent. Before I add anything else, I need to state, these are not laws of the universe, they are just orders of magnitude that have been found out through experience. The more you know about your flow, the more researched it has been, the more documented it has been, and the more precise the numbers are going to be to determine whether it's going to be turbulent or laminar. In all of this, the Reynolds number does not quantify turbulence itself. What it quantifies is the flow instability, like a probability that the flow is going to become turbulent. To explore the notion of flow stability or instability, I need a little bit more time. And I want to keep these videos short and digestible, so I'm going to stop here, and we're going to explore the notion of stability in the next video. So then, let's summarize what we have so far. A critical question in fluid mechanics is my flow going to be turbulent? To answer it, you need to quantify the Reynolds number. It's a simple formula: density times velocity times length divided by viscosity. We're not interested in the actual value of the Reynolds number, more in its order of magnitudes, how many digits it has. And we'll see in the next video that it's a measure for the instability of the fluid flow. So then, I think that's a good first look into the notion of turbulence prediction and Reynolds number. I hope you make good use of it, and I'll see you in the next video. Hi, I am Olivier Klein, and I'm recording a video course in fluid mechanics. If you find this video useful, check out the rest of them at learnfluidmechanics.com. I hope to see you there. Take care.